Good morning to everyone. In this session, we will discuss solar photovoltaic cells, which are one of the most important renewable energy technologies. Solar photovoltaic or PV technology converts sunlight directly into electrical energy. This topic is part of power electronics for renewable energy systems and covers the fundamentals, advantages, disadvantages, operating principle, and characteristics of solar PV cells. Efficient utilization of solar energy depends not only on the efficiency of the solar cell itself, but also on proper load matching in the external circuit. Solar cells are relatively expensive and contribute nearly 60% of the total PV system cost. Commercial solar cells generally have efficiency between 10 to 20% percentage. A solar cell acts as an electrical current source driven by solar radiation. Initially, solar cells were developed in 1954 for space satellite applications. Their terrestrial use gained importance after the oil crisis of 1973, which created a need for alternative energy sources. Under standard solar irradiation of 1000 watts per square meter, a typical solar cell produces about 0.5 volts and a current density of approximately 200 amperes per square meter. Solar cells are highly reliable and have a lifespan of more than 20 years. Since they require very little maintenance, they are ideal for remote and inaccessible locations where regular servicing is difficult. Solar photovoltaic system offers several advantages. First, they convert solar energy directly into electricity without any thermal or mechanical conversion process. Since they have no moving parts, they are highly reliable and require minimal maintenance. They operate silently and can be installed in almost any environment. Solar PV system respond instantly to sunlight and typically last for more than 20 years. Another major advantage is that they can be installed close to the point of use, reducing transmission and distribution requirements. Despite their advantages, solar cells have certain limitations. The initial installation cost is relatively high, making them less competitive compared to conventional power sources. Their conversion efficiency is comparatively low, which means large panel areas are required to generate significant power. Additionally, solar energy is intermittent because sunlight is not available throughout the day. Therefore, energy storage systems such as batteries are required, which further increase the overall system cost. The operation of a solar cells is based on the photovoltaic effect. When sunlight strikes the semiconductor material, protons transfers energy to atoms in the crystal structure. This causes ionization, generating free electrons and holes. A hole is the empty space left behind when an electron gains energy and moves away. These electrons and holes can move freely within the semiconductor material. However, if they recombine, the generated energy is lost. To prevent recombination, a PN junction is used. The electric field in the depletion region separates the electrons and holes, creating a useful voltage across the junction. As the generated electrons and holes enter the depletion region, the electric field forces electrons toward the N-type region and holes toward the P-type region. Since they become majority carriers in their respective regions, recombination is minimized. This leads to the accumulation of charges and the development of a photovoltaic electric field. Silicon is the most widely used material for solar cells. Other materials include gallium arsenide, amorphous silicon, cadmium telluride, and copper, indium, gallium selenide, each having specific advantages for different applications. Solar cells are manufactured by cutting single crystal or polycrystalline silicon ingots into thin wafers. The base material is generally p-type silicon. One surface is then doped to form an n-type layer, creating a p-n junction. Metal contacts are placed on both surfaces to collect the generated current. Multiple cells are connected together in series and parallel combinations to form solar module and panels capable of producing useful power. This slide presents the simplified electrical model of a photovoltaic cell. When the cell is not connected to any load, it develops on open circuit voltage determined by semiconductor characteristics and operating conditions. The equation includes constants such as Boltzmann constant, electron charge and temperature. The reverse saturation current and short circuit current depend on the manufacturing process and solar irradiance. This mathematical model helps in analyzing and predicting the performance of PV cells under different operating conditions. The VI characteristic shows the relationship between the output voltage and current of a solar cell. At zero voltage, the cell delivers maximum current known as the short circuit current. As the voltage increases, the current remains nearly constant for some time and then decreases rapidly near the open circuit voltage. The shape of the curve helps identify the maximum power point where the product of voltage and current is maximum. Maximum power tracking or MPPT technique are used to operate the solar panel at this optimal point. This graph further illustrates VI characteristics of a solar cell. The operating point of a solar panel varies the changes in sunlight intensity and temperature. Higher irradiance increases the output current, while higher temperature tends to reduce the output voltage. Therefore, the maximum power point continuously changes, making MPPT control essential for efficient energy extraction. Thank you for your attention. In this presentation, we discussed the fundamentals of solar photovoltaic cells, their advantages and disadvantages, the principle of operation based on the photovoltaic effect, construction details, and VA characteristics. Understanding these concepts is essential for designing efficient renewable energy systems. It will be happy to you. Thank you.